Alright friends, my name is Chef Machine and today we're going to talk about insertion sort. So insertion sort works in a similar way to how we sort playing cards in our hands. If you think about the way that we hold our playing cards, we want to sort them from highest to lowest. We might begin with our first card and we're going to say, okay, the second card is smaller than the first card, so I'll put it up front. The third card is right after the second card, and so on and so on. We basically divide our input into a sorted portion and unsorted portion, similar to selection sort, but the actual running of the algorithm is slightly different, as we're going to find out. So the runtime complexity of the algorithm is still of n squared, which is relatively slow, but the auxiliary space remains constant at O of 1. So the maximum runtime for this algorithm happens when the items are sorted in a reverse order, making us sort of shift our items the whole length of the items or n times through on every single loop, basically, as we'll see later. It is often ideal when the number of items in the input array is small, or when they're sorted or almost fully sorted. In other words, maybe two items are out of place. It is also slightly more efficient than selection sort or bubble sort in practical scenarios. So let's take a look at an example here. So we're going to start with the same input that we had in our selection sort video. So we have an input array of 23, 42, 4, 16, 8, and 15. Since we haven't started sorting anything yet, you can think of this whole array as unsorted. So on pass 1, we consider the first element to already be sorted, since it's the first element and you can't be out of order when you're the only one. And this is something we're going to see in most of our algorithms. So we'll mark that section as sorted. Then we'll have an unsorted section beginning with 42. Now, unlike selection sort, what we're going to do here is we're not going to cycle through the unsorted section trying to find the smallest element. No. We're going to take the first element in the unsorted sections, which is 42, and try to find a space for it in the sorted section. So here you can start to think of it a little bit as a sliding puzzle. I don't know if you've ever seen those as a kid. You have maybe a series of numbers and you have one blank spot and you kind of move the numbers around until you find such a place where they're all sorted and it all fits. So that puzzle is actually insertion sort. So we can see here that on pass 1 we're looking at 42, and 42 just so happens to be bigger than 23. So pretty simple here, we just move 42 from unsorted section to the sorted section, keeping its position in the array. However, when we move on to pass 2 and we look at elements at position 2, which is 4, so there's 4 here, 0, 1, 2. So 4 is actually smaller than both 42 and 23. And now that's where you can start thinking about this as a sliding puzzle. So what's going to happen here is that we'll have a blank space here, if you will, at 4, if you want to think of it, while 4 is still here. We'll create a blank space. So first, we'll have that blank space sort of after 42, which is here. Then we say, okay, 4 doesn't go there because 4 is actually smaller than 42. Then we say, okay, great. What about here? So we sort of move 42 out 1 to the right. And we say, okay, no, 4 is still smaller than 23. And we say, okay, great. How about we put it here? And we say, oh yeah, 4 does go here. So now we put 4 over here, and we move it out of here. And so now we have our sorted and unsorted portions once again. So let me just clean this back up so that it all matches up. So that's kind of how you can think about this algorithm. And so it goes on the exact same way with 16. 16, okay, is it bigger than 42? Is it smaller than 42? Yes. So we move 42 to the right. And we say, okay, 16, is it smaller than 23? Yes. So we move 23 where 42 used to be. And we say, okay, is 16 smaller than 4? No. That means we go back to this empty spot that's now empty, and we drop a 16 in there. So now we have 4, 16, 23, 42 in our sorted section, and our unsorted section remains at 8 and 15. And then we do the same thing for the other two items. So as always, I've provided links to actually the same 4 sources as the selection sort video. So we have a CS50 representation out of Stanford. We have my code school video with an explanation of insertion sort. We have Geeks for Geeks video for insertion sort, and of course the Geeks for Geeks written explanation for insertion sort. So now that we've done that, let's take a look at the actual code. So as always, this is written in Visual Studio Community for Mac and C#, as all of my algorithms will be. So we begin with our public void run, which you can think of as public void insertion sort, as all of my algorithms will actually utilize this run method, just for my own convenience. So we begin with setting the length property, which is just for my convenience to make my life a little bit easier. So we set input array.length equal to length. Then we begin to actually create 2 loops. The first for loop is going to be looking at the individual items in the array. So this actually sort of tells you where the sorted and unsorted sections are. And you can see on pass 1, we already have a sorted element, which is why we begin with int I equals 1. So since 0 elements can be sorted and unsorted, and a single element is always sorted, we always begin at int I equals 1, which is basically this, at 42. That way we can actually compare it to the sorted section and actually start the algorithm and make it slightly more efficient. So we begin there. We create a variable called key, which is input array at I. So basically we say our key, if you think back here, is 42, right? And we say, okay, well, let's take a look. Our variable j, which is going to be the index for the first element on the right of the sorted section. So it's the first element on the right of the sorted section. The element sort of closest to the first element of the unsorted section, which is what we're looking at with j. So j is basically equal to I minus 1. So 1 to the left of the element we're currently looking at. And we say, okay, while that element is greater than or equal to 0, and the key that we set up here is smaller than input array at j, we basically are going to continue to move to the left while sliding the pieces at that section to the right. That's the best way that I guess I can explain it. So essentially we're going to continue to move left until we hit 0, which is here, beginning of the array. And we're going to continue to move left until such a time that our key, which is 42, okay, is smaller than input array at j. Okay? So that's basically what we're going to do. On this first pass, we're not going to go into this loop at all. Why? Because our key is bigger than input array at j, and we only have 1 item in there. So, just for this first pass, I'll explain that we will not make it inside of this loop because this condition will not be satisfied. So what we're going to do is we're going to say, okay, input array at j plus 1 is equal to key. So basically, this is our j, this is our j plus 1, and that becomes our key, 23, 42. Pretty simple. So 42 remains where it's at because we went back 1 and we went forward 1. We went back 1 in order to compare it to our sorted array. I went forward 1 because once we find a place where, if you think about it as a sliding puzzle, you slide, 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 items to the right, and then you kind of get to a point where the element that you're looking for is bigger than the element on the left. So now you have to go back to that open spot and kind of drop your number in there. That's the best way that I can describe that. And so let's just go on to the next item, which is 4. So 4 actually will make it inside of this array. So 4 goes in and it says, okay, I'm 4. Let's take a look at, j equals I minus 1. Let's take a look at 42. That's my key, right? So, sorry, my key is 4, but now my index is I minus 1, which will be 42. So it says, okay, is my key smaller than is 4 basically smaller says, yes, it is smaller. So what we're going to do is where 4 used to be will now be 42. So 42 kind of moves to the right and takes a place of 4. So 4 is gone. It's only now in memory in this key variable. Okay? And we just moved 42 right 1. Okay? So then we go j minus minus, which is going to move us to the left even more. So now we're looking at 23, and we say, okay, is 4 smaller than 23? And we say, yes, of course it is. So now we move 23 to the right. So where 42 used to be, we now override it with 23. So now we have this open space at 23, and we say, okay, hey, is j equal to 0? It is. And we say, okay, bust out of that loop. And because j is equal to 0, and actually, because we're in this loop, it would be at -1 because we just completed this loop. We went into the loop, we set this to -1, basically it's no longer at 0, we come out of this loop, because that's how we come out of it, and we go back to 0 and we set the key on the 0th position. I hope that made sense. And if it doesn't, please watch the CS50 video, my code school video, G4G video. They have an incredible job animating this for us. But essentially that's it. And so once we go through this for loop and we finish, that means we are done with our sorted section is now as big as the length of the array. And that means the algorithm completes. So now let's go ahead and run the algorithm. Let's take a look. We got 4, 8, 15, 16, 23, and 42. So the outcome matches what we should have gotten, and we are done with this algorithm. Thank you very much for your attention, and I hope to see you again next time. Bye.